staring at the answers. Okay. All right, what's the progression of functions that fulfills the goal? Here it is. This is part B of number 1. 1 point each. There's no partial credit. Everything's worth 1 point. So this is 5 total points. 1 point for each one. 1 point for each one. What's that first function? Now the description's up above. What's that first function? Exact rate of change. Exact rate of change. 1 point. You have to have all the details. If you just wrote rate of change, -1. It's the exact rate of change. What's R? Approximate rate of change. That's a point. What is A? Approximate net accumulation. 1 point. Got to have all the Got to have all those words. And then exact net accumulation. And then exact total accumulation. So we are up to 10 points so far. 1 point each. No partial credit. And these have to be perfect. If there's any detail missing on any of those, -1. Okay, so transitions. Transitions. What's the transition from exact rate to approximate rate? Build a step function to simulate R sub P. Build a step function. So if you said something about a step function or constant rate to mimic the original function, that's worth a point. That's the point. You're drawing constant rates, a new function made of constant rates to try to reproduce the exact rate function. Right? 1 point or nothing. So it has to be something like that. Okay, next one. So how do we get from approximate rate to approximate accumulation? This is the big idea here. Mathematical idea is dy equals m dx. Accumulate changes according to R. dy equals m dx. That's what you do to build up the A function. Rate times change, and accumulate them, right? Add them up. Something like that. 1 point or 0 points. All right, so this is what we're going to talk about more later today. All right, and then the last one is how do we get from exact net to exact total accumulation? You're going to add all the previous accumulation. Add the previously accumulated amount. So whatever was accumulated before, we're going to add that to our net accumulation function. That gives us exact total accumulation. Okay, so we're up to 13 possible points. Add 7 to your current score. Just 7 for free. Thank you. We're going to start class. Here we go. As you're passing, we're going to embark. So here was that exact rate function. And one of the first things you did was you looked at a constant rate over the first 0.2 of either 25, 45, or 60, right? So you found out what would the new population be at those particular constant rates. And then I asked you, which one of those might be a good way to estimate the actual rate, this changing rate, right? It starts around 30 and goes up to around 60. So which one of those, if we could choose one rate, which would best simulate the actual changing rate? Which one? The one in the middle, right? This is way too low. 25 is too low. 25 is too low. It's because it's lower than every rate that you see in that interval. 60 is higher than every rate that you see in that interval. 45 would be something like 45 would be the best we could do if we had one rate of change to simulate the real rate, this changing rate, in that 0.2 months. Okay, so we're going to keep that one. And then you had to continue that exercise of making the function R. So here's my version of R. Not that. Here's my version of R. Okay? What am I doing? Again, what is R? It's a function made up of constant rates trying to be like the original rate function as best we can, right? As best we can. So when you were doing this, did some of you have an image like this? And like this? Okay? So this is, if you thought about areas, I want to do my best to try to say, No. Okay? So, yes, we're going to get to area, but in order to talk about area, we first have to get set that this is not about area. It's not about area. What does area have to do with population of insects? It doesn't have anything to do with population of insects, right? So what is this? This is again, those black lines are a new function trying to be like the old one, but with constant rates. This is not a function. This is not a function, right? So we created a simulated function. So in order to talk about area, we first have to understand that really it's not about area at all, okay? Okay, so going back to that. So let's just talk about how would we then use, this is our this is our R sub P, right? And then the black one that I drew would be R, right? And so what would A, so there's just some function A, right? Some function A. So let's talk about a particular value of A, say A of 0.63. And then by kind of talking through the calculation of A of 0.63, then we can talk about what the structure of the A function is. So how would we go about calculating A of 0? First of all, what is A of 0.63? What does that mean? What does that mean? So he said the approximate accumulation, so total or net? Approximate net accumulation of insects at 0.63. And it's approximate because it's based on R, not R sub P, right? It's based on the R function, not R sub P. And so how do we do that? How do we get, based on R, how do we come up with a net accumulation of insects at 0.63? Yeah, so we want to get the accumulation in this first interval. What's that going to be? 45 m dx. And then we have some accumulation from the second interval here. Looks like I'm saying about 42. So at the constant rate 42 times the change in time of 0.2. And then 21. Does that seem fair? So what's happening here? So we're accumulating these changes given a constant rate, right? So when constant rate of change, we know that the change is the constant rate times the change in x. And then plus, so if I'm doing a 0.63, so what do I have to do next? So it looks like about 16 maybe? Is that fair? Rate of change about 16 times 0.2, right? Times 0.03. So now that accumulates all of the change in population starting from 0 up to 0.63. So notice that we're doing the same thing over and over again here, but there's the rate changes, right, in these first three. And so when you keep summing the same thing or something very similar over and over again, we have this symbol for that. So now we're going to talk about what's the structure of this function, right? So now thinking about any x value, thinking about x increasing through the months, and this function A giving us the approximate net accumulation for every x as x increases through the months, right? So what does that function look like? It looks like a sum of what? R for different x's, right? Times delta x. In this case, the delta x was 0.2. And we call this the accumulation from all the completed intervals. So for any given x, you have a bunch of completed intervals. And those all have the interval width of delta x. Then there's also a little bit more accumulation, right? And that's the accumulation from the current interval. So let's call that Rx, say current. And now this little amount, so where these fixed intervals were delta x, in the current interval, we think about that x value sweeping through the current interval, and the amount of change that we have in that current interval is, anybody? Did we talk about this? That's what we're going to call dx. So dx is going to be this changing. So you got to think of that as a variable, right? That varies through each interval. So from here to here is dx, and that as x increases, that increases through each interval. And when you get to a new interval, dx starts over at 0 and increases through the interval until you get to the next interval. Then dx starts over at 0.
So is that x minus 1 up there?
No, x, this thing here, x sub I, this here?
Yeah.
Yeah, I meant to write x sub I. It's like, so you have different x's. That's better. Okay. And then I is going to increase from 1 to the number of completed intervals. So we're just kind of building a loose structure. So this is not the function, because the function itself would have to be written as a formula of x. So this is just the structure of that function, okay? And that's as far as we're going to go in review, okay? So we have the sum of the little bits of accumulation from the completed intervals plus a little bit more accumulation in the current interval, right? And that's going to have a shorter interval of x's. And we think of that as x increases. As x increases through an interval, dx likewise is a variable increasing through the interval. Okay, questions on that? Okay, so let's look at, oh wait, can you help me? Yeah, question. X current. So I'm just like the current x, like the x in the current interval. Yes, sir.
I'll look at the 45 and 42.
That's so I'm estimating that, right? This is our. Everyone might get something different, but this is just my best. It's my best guess at if I have in each interval, if I have one rate that I have to pick to simulate the blue rate function, I'm just going to pick one, right? So 42. So I picked right about here. So from point 2 to point 4, I see that the rate goes from here to here. And so I just picked a value to try to best reproduce that changing rate from there to there. But I only get one rate to do it, and so I said that's about 42. Is it better? Okay. Okay, so let's look at a new example. Go to the sand unloading side. Okay, so this graph is showing, we're unloading sand onto a scale, and this graph is showing the rate of change of weight as a function of time. And that rate of change is in 100 pounds per second, and the function time is in seconds. And what's our goal? Our goal is to come up with, what would our goal now if in our current journey here? We have the rate of change of weight unloading onto a scale, and we want to know. So what do we really want at the very end? We want a function that gives us the exact total weight on the scale, or exact accumulation, exact total accumulation of weight on the scale. Those are almost one and the same, right? Those are just one constant away from each other. Okay, so let's see. Is there an extra one back there? No, I got it. I'm good. No, I need it. So the first thing to do is say what's going to be our quantity of focus here. What's our quantity of focus? So you're going to label the axes, okay? And then what's the dependent variable quantity of focus in this situation? So what am I going to put on this x-axis here? He wants number of seconds. Agree with that? Yep. What about the other x-axis? No, this x-axis. Also seconds. That's our x quantity is what? Number of seconds since the sand started unloading. Okay, number of seconds since the sand started unloading. Okay, how about the y-axis on the left? Yeah, and so since these are 1, 2, 3, 4, 5, it's actually going to be 100 of pounds per second. So hundreds of pounds per second is going to be our unit there. And then what's going to be our unit on the y-axis on the right? She wants hundreds of pounds. Agree with that? So 100 pounds. Each one of those tick marks is 100 pounds. Okay, so the first thing we want to do is let's estimate or just make a sketch of the goal, right? The goal is what? Exact net accumulation of weight. Exact net accumulation of weight. That's our goal. So can you just briefly sketch what you think that would look like? And we're going to sketch it on the right, right? I put it up faintly on the graph. I put it up faintly. Can you see it in the back? Does it show up? The gray? The light gray? Okay. So we know this thing exists, but it's kind of like we haven't made it yet. Does that make sense? We know it exists. Our goal is to actually mathematically create it and to represent it mathematically. Okay? So this is our end goal. So now I'm showing over here on the left, I'm showing which function, rather than the exact rate function emerging, I'm showing which function emerging now. R, which is approximate rate. So you got some questions about that in the second number 2. I was rushed when I made this. In the second number 2, you got some questions now that I'm showing you this, the function R being generated. So you can answer those questions, think about it, and then compare with people next to you. Oh. Okay, before we do that, so what do you notice that's different about this one than all the ones we've done so far? So there's something different about this R function compared to the ones we did the flag, and you guys did the insects for homework. What's different about this one?
We're taking the leftmost point of the interval as the average rather than something in the middle.
Right. So rather than so far in each interval, we looked at the interval, we looked at the sweep of the rates, and we tried to give our best guess at a single rate that would simulate that. So this is a different strategy. Rather than trying to eyeball and all getting something different, another way to create this R function is take the rate of change, the actual rate of change on the left side of the interval, and make that the constant rate on the whole interval. That's what this is doing. So this is more systematic, and if we all do that, then we'll all get the same thing. Does that make sense? We'll all get the same thing. For instance, this rate, this highest rate up here, will be, the value of that rate will be R sub W of what? So what's the left side? Yeah, so if it's hard to see, these intervals are 0.3 seconds wide. So this fourth rate up here is going to be equivalent to the actual rate at the left side, which would be R sub W of 0.9. and that becomes our R for the third interval, fourth, sorry. Is it cool? Does that make sense? All right, so go. How are we doing on those questions? So discuss those questions on the. You can do them both. So starting value for the accumulation. What's implied here? 0. So starting at 0. Duration of the intervals there, what we call moments, 0.3. Number of completed intervals, if we're talking about 0.8. 2 completed intervals, right? And then what would the current interval be if we're talking about 0.8 from what to what? 0.6 to 0.9, right? So the current interval, even though it's only to 0.8, the current interval goes from 0.6 to 0.9. And then what's the value of dx if we're at 0.8? 0.2. Do you follow that? Anybody have a question? Okay, so then in terms of the answer to number 3, I've written it up there. I said A of 0.8 would be the rate we have in the first interval. So this subscript is just talking about which interval, okay? The rate from the first interval times the width plus the rate times the second interval times the width plus the rate at the current interval. But then that one will be times 0.2, right? So then let's rewrite here. Just again, what would AX be? We're going to sum together. Now thinking about all values of x, any value of x, how would we calculate the approximate net accumulation? So it would just be the sum of all the accumulation from the completed intervals plus the R in the current interval, good, dx, right? So dx, we think of dx as this, it's a variable in the current interval. How far into the current interval are we? And that changes. It starts at 0 and it goes to all the way to 0.3, and then we get to the next interval, and that dx goes from 0 to 0.3 again. Okay, and so when we do that, so is this a function, what will it look like? What will this a function look like? Will it be a curve like that? Series of lines, right? It's a piecewise linear function, and will this, in this particular case, looking at how R compares to RW, will it be right on this, kind of matching the curve, above the curve, or below the curve? So how do our rates compare? Yeah, so all of our rates, by using the left endpoints at the beginning here, all those rates are lower than the actual rate in every interval. Do you see that? It's all those blue ones are below until we get to about 1 second. But then we're so far behind, right? So then the net accumulation approximate is so far behind that it might catch up, but it's going to stay below. So it looks like this. So not bad, right? So knowing where we're headed for this gray curve. That's what we're trying to create. We know it exists, but we haven't gotten there yet. Here, using intervals of 0.3, we get a pretty decent approximation of, what do we call this? So the gray one's going to be called what? It's the exact net accumulation. That would be our AW, right? And so A is the purple one. Here's the general structure of that purple one, A. Okay, so we mentioned it earlier. Then how do we get from A to AW? What's our next strategy? Okay, so we're currently our moment intervals are 0.3. By making the interval width smaller, the new R function
It'll get closer.
will do a better job of reproducing R sub W. And therefore, the A function will do a better job of reproducing AW. So let's go, say, to 0.1. So here's 0.1. So notice all those little blue steps. Now the interval width is 0.1. Those little blue steps are doing a better job reproducing R sub W, the red one. And then look at the resulting net accumulation. It's getting pretty close. So we can go really close. So when you make delta x super small, so in the back of the room back there, what does that look like on the left side? What does that look like to you? Is that a curve? Is that a nice smooth curve back there? Is that what it looks like? Let me zoom in on it. Watch. I'm going to zoom in on it. It's still a whole bunch of little constant rates. It's still a whole bunch of little constant rates. This is now we're talking about 0.01. 0.01 is, so with a delta x of 0.01, we're getting really, really close to very perfect, almost perfectly reproducing that rate function. From the back of the room, it probably looks like very much like the curve we started with. Okay, so I'll go even smaller. I think I got 0.005 here. So here's 0.005. 0.005. Our constant rate function is virtually the same as the original rate function. And look at our net accumulation. Can't even see the difference, right? So what we do is we make delta x small enough so that we can't tell the difference. So we can't tell the difference between exact and approximate, and then we call that exact. Okay. So what happens to the current interval, a smaller width interval, right? It's not a smaller width interval, but this virtually, as delta x gets small, as delta x gets very small, this kind of just goes away, right? There's no real difference between the current interval and completed intervals. They're all so small. This is the big punchline here. So as delta x gets small, capital AX becomes what? A sub W of x. This 0.3 goes to 0. And so then what does this become? So we have it. So for super small intervals, we have a different symbol for summation. It's not Greek S, but German S, which is what? German S. And then all these separate constant rates, now because it's so small, it's kind of like we have the whole continuous rate function. So rather than the R function I have, don't miss this. This is what we've been working for 3 days. R sub W of x. So when delta x gets super small, the constant rate function then kind of morphs into the continuous rate function. And our delta x is our small intervals. So how do we transition from approximate net accumulation to to exact net accumulation? Well, we make delta x very, very small. And then our summation becomes integral. So this is still summation, but now we're summing up a gazillion little bits of accumulation, right? As x is varying through super tiny intervals, and we're accumulating these itty-bitty bits of accumulation super fast, and a whole mess of them. Question back there. Someone had their hand up. Yeah.
What does it say after the A? So what?
W. Okay, so I just got one slide to kind of summarize this. So don't take notes. Don't try to take notes. Take notes on the video if you want. So our approximate net accumulation function we said was this: sum of completed intervals plus a little bit more in the current interval. And so we said as those intervals get really, really small, there's no difference between completed and the current interval, and summation becomes integral, and our step rate function just becomes the whole continuous original rate function. So notice this. So we had this progression of functions, right? But notice that this statement right here takes us directly from what? Exact rate of change to exact accumulation. See that? So we've paid our dues. We know the nuts and bolts in between, and it earns us the right now to just write down what exact net accumulation function is given exact rate of change. And then what about exact total accumulation? So if there were P 100 pounds of sand originally, then what would the function W be? So if before we started all this there were P 100 pounds of sand on it, then what would the W function be? All the previous accumulation, P, plus the exact net accumulation, which is our integral function. So we made it. Look, you know how fast a quantity is changing at every moment? And we want to know how much of it we have at every moment. And that equation is the kind of the pinnacle of answering that question. All right, on the back of that green sheet,